This is a talk about the paper called StateCharts, A Visual Formalism for Complex Systems by David Harrell. It was printed in 1986. I'm using a PDF that's called StateCharts Presentation 2020, has 33 pages. I've also posted a larger PDF containing all the missing slides that I'm going to skip over in this presentation. I've got an annotation for every slide. Page 2 of the PDF is a little bit about me. I'm an electrical engineer. I also studied core physics. I did a lot of work with compilers, operating systems, domain-specific languages, embedded systems. I ran my own software consultancy for about 25 plus years. I first read this paper in 1987. I applied some of the principles in this paper to a project at the time. We were replacing programmable logic controllers, PLCs, on injection molding machines. PLCs were too slow at the time. We used a four-headed 68,000, wrote StateCharts as device driver software underneath the operating system. My current interests are using diagrams as syntax for programming languages, expressing design intent, which some other people call architecture, but I find the word architecture is overloaded and I try to use the word DI instead. I hope that you'll get a feeling for what DI is when you read my stuff. I'm also interested in turning software development into engineering, a bunch of layers of engineering, architecture, guarantees, actual implementation, and testing and stuff like that. Page 3 is a quick overview of the paper itself. The paper is 44 pages long. It has 49 figures. It talks about hierarchy, concurrency, communication, structure, and control flow. The paper has 9 sections, and in my opinion, the meat of the notation is found in sections 2 to 5. Page 4. The notation was originally used for an avionics closed source project. I think it was for the military. In this paper, the author describes a citizen digital watch, which was popular at the time. He reverse engineered the functionality of the watch and then compared it against the user's manual for that watch. The conclusion was that he feels there was an error in the documentation. I conclude that this was probably designed by committee. We'll see later what I mean by that. Introduction, page 5, then page 6. Page 6 contains a simple state diagram with 3 states on it labeled A, B, and C. They are the rounded rectangles. Transitions between the states are shown as arrows with Greek letters representing the pieces of code that cause transitions. So from state B, we might go to A if we see an alpha event. From B, we might go to C if there's a delta event. From A, we would go back to B if there's a beta event. And from C, we would go back to B if there's a beta event. Notice that there are no beta events emanating from B, so it ignores all beta events. Those are only valid in states A and C. State A can go to state C on a gamma event guarded by a predicate P, which is a true or false. If a gamma event happens while the system is in state A, and at that moment in time, the predicate P evaluates to true, it's just a piece of code, maybe a piece of JavaScript or something, then we would take the transition from A going to state C. Notice that there's no transition going from state C to A. The only way to go there would be to follow back to B and then back to A. Again, this is just a simple example of the notation. Next slide, page 7, state levels, clustering and refinement. Page 8 shows figure 2 and the synopsis of figure 1 in the upper left-hand corner to remind us what was there. What he's showing here is what he calls clustering. If you look at figure 1, you'll see 2 transitions on the beta event. In figure 2, he collapses that down, creates a new state called D, and has only 1 transition from D to B on a beta event. What this is basically saying, it doesn't matter if you're in state A or in state C. If you see a beta event while you're in one of those 2 states, then we transition to B. He also shows more detail on the alpha event, the delta event, and the gamma event, which we've already discussed. Next slide, page 9, shows figure 3 and figure 4. Figure 2 is in the upper left-hand corner. He's using different levels of elision to make it possible to discuss different degrees of complexity of this state chart. Figure 3 shows only two states, B and D, shows the transitions between them. It doesn't show any breakdown for state D and doesn't show any breakdown for state B. Figure 4 shows that D breaks down into states A and C, but doesn't show any of the details of transitions between them. Next slide, page 10, shows a photograph of the Citizen watch that he was using and his sketch of the Citizen watch that he was using. You will note that between the time that he wrote it and I found the photograph, the time display was moved from the bottom to the top. The 4 buttons are still there and they're labeled A, B, C, and D. And the 4 sub-windows, basically it's an LCD display with a home screen, and you'll see how that works in a moment. Next slide, page 11, shows a new notation in his notation. A dot with an arrow means the default transition. So 6I shows that the system wakes up and goes to state A by default. And 6II says it goes into state D.A by default, passing through the wall of state D. And 6.3 says 6III says the same thing, except it does it by cascading defaults. The first default goes to state D, has a default in it that goes to state A, and the end result is the same as in 6II, that we end up in state D.A by default. Next slide, page 12, shows a system that might have state explosion problems, but he's contained the state explosion by wrapping a state called alarms beep around 3 other states, alarm 1, alarm 2, and both. And each of those states might go to display if any button was pressed. What he's done is he's wrapped a state around all 3 of those inner states and written only one transition called any button pressed. That means go from any of those states into displays if any button was pressed. Likewise, he's got a transition that goes, if one was in the state alarms beep for 30 seconds, there's a timeout that happens and the system goes from state alarms beep, doesn't matter which substate it was in, and it goes to display. And he's got other detail on this diagram that shows how to go from state to the various substates of alarms beep. Next, page 13, figure 9, shows more detail of the display state. It chops the display state up into 6 pieces. If we are in the home screen, shown by the default is the time display. If we're in the time display and we hit the A button, which was the top left button, then we go to the alarm 1 state. If we hit the A button again, the top left button again, we'll go to the alarm 2 state. If we hit the A button again, we'll go to the chime state. If we hit the A button again, we go to stopwatch state, and if we hit it one more time, we go back to the home screen time. If we're in the home screen time and we hit D, we go to the date screen, and if we hit D again, we go back to the time state. And if we go to the date state on a D button press and do nothing for 2 minutes, then a timeout will force us back to the home screen, and we've all seen that in normal LCD displays on controllers such as your thermostat for heating and cooling in your house, so that if you leave it alone, it'll go back to a default window and show you a home screen. Next page is page 14, figure 11. Here he shows a new piece of notation called the history transition. Figure 11A shows history, one level of history, which is a circle with a capital H in it. And there we might be in state K.G or K.F. If we leave state K, the system will remember whether we were in G or F. But let's say it goes back to K.F. It will take the default transition in F and go to C, K.F.C when we come back. In figure 11B, he shows deep history, which is an H star. And there it remembers which substate of K.F and K.G we're in. So the default only works the first time we come in when history is clear, and otherwise it remembers, let's say we were in state k.f.e, and we leave and we come back, it'll go to k.f.e again through deep history. Next page, figure 13 shows even more detail of the display's state. I won't spend much time on this. You can read my annotations for it. Next page, 16, he shows a new notation for economical representation using dots. A and B are valid notations, C is invalid. If we look at figure 17a, what that says is that the lower left hand, if we're in the lower left hand state and we see an alpha transition, it goes to the dot, and the dot immediately goes to the upper state without waiting for another event. So the A event drags the bottom left state into the top left state. Likewise, the bottom right state transits on a beta transition. 17b says that both bottom states transition on an alpha and they go to the upper state. And version C, 17c, is really just 17a with all the arrowheads pointing in the opposite direction. 17c is a contradiction and is illegal. Page 17, figure 18, shows more contradictions, things that can't legally be drawn in his notation. The first contradiction is the transition on alpha events. If you look, you'll see there's two alpha events drawn on the diagram, one going from B to the state to the right, and one going from B.C.A to the state on the bottom. That's ambiguous, and the system can't decide which one of those is to be taken. The editor cannot allow that to happen. The other contradiction is that the big state B has two default arrows, one going to B.C.D and the other one going B dot to the unnamed state at the bottom. You can only have one default per state at most, and that is a contradiction. In my opinion, the first contradiction, the two alphas, can be handled by the editor of the diagram editor that makes it impossible to draw an alpha transition in the child when it's already been drawn on the parent state B. And I think that would fix the problem. But he leaves that as a contradiction. Next slide, 18, page 18, 3, orthogonality. Next slide, page 19, figure 19, shows the Y state chopped up into two with a dotted line in between the two states A and D. Those two states are orthogonal and run at the same time. There's at least two, if not more, ways to implement that. One is to assign threads to state A and another thread to state D, and to start them up at the same time and to let them finish at the same time. As soon as you start Y, we see both A and D have default states, and that would be where the threads would go. Another one will be shown in the next page. Another solution to solving this problem will be shown in the next page without using threads. What this shows is that one can decompose a problem solution as multiple orthogonal machines, or simultaneous states as he calls them, when it makes sense to talk about them that way. If this weren't a toy example, one might look at the A state and say, by default it goes to B, and if there's an alpha transition it goes to C, and if there's a beta event and the other machine is in G, then we go back to B. And the D machine likewise has various transitions shown on it. Next page 20, figure 20, shows a completely flattened version of figure 19, where the state names have been changed to include commas. So there's B, E, B, F, B, G, and likewise C, E, C, F, C, G. And that shows if you work it out, you'll see that This shows the same state transition diagram as that of figure 19. One can see that already figure 20 is less understandable than figure 19. And in non-toy examples, real examples of this stuff, using simultaneous states makes designing a lot simpler. Next, page 21. He's beginning to show the specification of the watch from the top down. So figure 26 is the very top. Figure 27 is mid. Figure 20 has more detail. Figure 26 shows the very top of the watch diagram. And the watch basically has two main states, dead and alive. And the default is the dead state. If we insert a battery, the watch goes from being dead to alive. If we remove the battery, it goes from alive back to dead. And if the battery dies, it goes from alive back to dead. Figure 27 shows the alive state chopped up into 6 other simultaneous states. And then figure 28 shows even more detail. Again, it depends on who you're presenting this to. An engineer would want to see all the detail. A customer or a stakeholder would want to see only the top levels without all the details. And it makes sense to show a customer or stakeholder levels that have the details elided, so they can comment on how the design is going. Next, page 22 shows figure 29. This is a very common pattern where 2 buttons B and D are pressed at the same time and should produce a beep. In general, one would say that the beep test function starts at the top state 00 and it ends up in the beep state beep at the bottom. Humans perceive simultaneous events happening in anything less than 20 milliseconds or less appears to be simultaneous to a human, whereas to a computer, it can differentiate times of microseconds and nanoseconds. When a human thinks he's pressed both B and D, B was the top right button and B was the bottom right button. If you press both of those at once, the hardware sees either the B coming first or the D coming first. And this diagram solves the race condition of which one came first at the hardware level. And the way to solve it is by adding 2 more states, saying, looking at the left side, if we think we saw B first, then we go to the state 10, and then we see the D in rapid succession, then we go to the beep state and we beep the beeper. What he's labeled as D hat and B hat are someone releasing the buttons. So if you release both buttons, let's go back to the pushing both buttons at once. If you see both buttons pressed, another option might be that the D looks like it came first, then the B came first. And the way to solve these kinds of race conditions is to allow only one event to happen at a time, even if they look to be simultaneous. On the right-hand leg, we handle the case where D comes first, then B comes. And that ends up in the beep state, just like the other B followed by D rapidly, it goes to the beep state. If we let go of the D button and then the B button, we go back to the top. If we let go, and the hardware thinks we let go of the B first and we let go of the D second, we still end up at the top. This pattern should be memorized as one of the patterns that will help disambiguate such hardware level race conditions. Other things that we call race conditions in software come from accidental complexity of using shared memory in conditions where we shouldn't have been using shared memory in the first place, like multitasking. Next page, next 23, the full diagram for the digital watch. I won't spend time on this. You can stop the talk and enlarge this and see that it does solve the problem. The place where Harrell thought that the documentation didn't follow the actual implementation can be seen as a notch in one of the upper states. I think it's called regular, in the upper left middle. And again, if you analyze this diagram, you'll see what he thinks that the thing actually does versus what it was documented to do. And I think one will see that it's probably the design was done by committee, sort of airy-fairy on pieces of paper or on chalkboards. They probably didn't even have whiteboards at the time. And then the implementers implemented the hardware in a certain way and found that they had to resolve some ambiguity in the system. Next page is page 24. Additional state chart features that weren't shown in this watch example. He didn't touch on conditionals, selection, timeout, and unclustering. Next page, actions and activities. Next page, figure 37, page 26. He shows entry and exit code, where, for example, if you look at the A state, one of the deeper states, it has something called entry and a big capital S. That capital S represents a piece of code, I don't know, a piece of JavaScript or some Java or something. And so the capital letters in entry and exit and throughout mean pieces of code, whereas the Greek letters in those things mean actual events that caused the state to change. So if we enter the A state, we execute the entry code S. And if we enter from C going through A into B, then we cause the entry code S to happen. We cause the entry code V to happen, which is part of B. And when we execute a transition from B to F, he hasn't even labeled that with an event. Again, he's just trying to make a point here. I'm trying to keep details off the diagram so that if we if we go from B to F, the throughout X code gets executed, but the entry of S does not get re-executed. If we leave the state A on a gamma transition for any reason, we will execute the code labeled W. And likewise, to the right, we see D going to E on a beta transition. And if that happens, the E state has an entry code of U that will be executed. Next, page 27, 6 possible extensions to the formalism. I didn't feel these were very important, and I skip over them. I have annotated them in another PDF file if you want to follow the paper more closely. He talks about parameterized states, overlapping states, don't repeat yourself, called DRY, incorporating temporal logic, recursive states, probabilistic states, etc. Next page, semantics, is page 26, section 7. He wrote another paper and references it as number 15 in his references to this paper, where he takes apart the semantics of state charts. He uses something called microsteps. Next, page 29, related work. He talks about the state explosion problem, SDL, ATNs, Petri nets, CCS, HORS, CSP, communicating sequential processes, Estral, and sequence diagrams. Let it be noted that Harrell went on to write more papers and a book about sequence diagrams. I guess he found those more interesting. And the next, page 30, is practical experience and implementation, section 9, which is dated by definition since the paper was written in 1986. At that time, there were 4 places one could find state charts. One was in the product called StateMate 1, iLogix, and IBM Rational. Those have faded into the sunset. We're left with UML2. UML2 does incorporate state charts. Next page, 31. Just touch on my experience in actually using this stuff in real life. I found that I could take the diagrams and compile them to code as long as I imagined diagrams not to be composed of pixels but to be composed of glyphs. The glyphs to represent these diagrams consisted of rounded rectangles, arrows, text, and dot. Each one had a 2D XY component to them. I then used inference to derive all the other properties that were interesting to me and would make this stuff fit into a regular syntax that could be parsed using normal compilation techniques for 1D languages that process text. I happened to use Prolog because it was a convenient way to search and do inferencing because of its backtracking. I imagine that Minicanran, which is a more recent version of relational programming, can be used, but I haven't done it. I imagine various forms of pattern matching can be used to derive these properties. I've actually done the inference using a more normal language that had loops. I just used loops within loops to do inferencing and pattern matching and matching over a whole matching space, which is what Prolog really does in the end. I will present another paper on understanding Prolog. I found that I believe that comments don't work. Whenever there's a rush on a project, the comments fall to the wayside and get out of date very quickly. Using compiled code is the only stuff that is meaningful. If one can compile diagrams which describe things that code can't describe, then there's more than one way to store design information and to compile it. I use the word compilation instead of modeling to keep me honest in choosing notations that can only be compiled to code, whereas modeling, such as the Universal Modeling Language, UML, allows for things that can't be compiled, like pictures of clouds and stick people and things like that. I also found that errors are not in any way special, and there was no need in my notation for throw and catch. Errors are simply other events, and you can draw them transitioning between states, and using Herald's notation of encapsulating states, there's no need for extra syntax to handle throws and catches.
That was a pleasant surprise in that it made my languages much simpler to implement and
think about. I found that this notation was understandable by management and stakeholders. It's what Agile was trying to do, but they do it in a hand-wavy way, and I insisted on being able to compile my diagrams. This notation gives a way to add structure to control state. There's a number of ways that state can impinge on a program. There's no need to throw state away. Object-oriented found a way to encapsulate state. Herald StateCharts encapsulate state for control flow. The problem that we need to solve is spaghetti anything. Structured programming back in the 70s brought
structured programming control flow
to deal with spaghetti use of go-tos. We need to worry about spaghetti message passing and spaghetti architecture, spaghetti types, and so on. The stuff like what Herald did in this notation is where we'll need to go. Next, page 32, my experience continued, is Herald's concurrent states, or what he called simultaneous states, I lifted into a completely different notation. That notation looks a lot like flow-based programming, FBP. And it turned out, by lifting it, I found that I had a simpler language for handling state diagrams and a simple language for handling concurrency. Both languages were simple enough to compile from diagram form into executable form. While working on this paper analysis, I discovered that there was a GitHub for StateCharts and that W3 talks about XML for StateCharts. I also note that the Dracon editor, sourceforge.net, is also another interesting graphical notation that compiles to code. And the very last slide, page 33, is my email and my GitHub URL.